I am Casey Castelnuovo, and today I will present our vision paper, A Theory of Dual-Channel Constraints. Models of code based on program analysis and statistical properties have different strengths and weaknesses, including whether learned properties are sound or probabilistic, their ability to scale, and where the information is extracted from. Research to combine and exploit these methods is still early on, and so we'd like to present a framework for thinking about code that will be able to take advantage of the signals from all sources. We first note that code is written for two audiences: the machine that must execute the code correctly, and other programmers who must be able to read and maintain it. However, how is code processed by each of these two audiences? For this, we introduce the idea of two channels of code. Code has a formal algorithmic channel, which represents the computable meaning of the code, and it has a natural language channel, which consists of natural language meanings and cues that help programmers approximate meaning. For example, this function is the sieve of Eratosthenes, and the natural language clues include the names of the variables, the way the code is laid out on the screen, and potentially even small ordering patterns. Any of these can help programmers understand that this is a function that computes primes without having to compute each step mentally, which may be cognitively expensive. Key to relating the dual channels to the two audiences is that these information channels are used asymmetrically. The machine only uses the formal algorithmic channel, while humans use both, and when writing code are simultaneously trying to make the code correct and easy to process. Our near paper calls for exploiting channel interactions, as previous research has tended to leave information off the table. Each channel constrains the other, with the algorithmic constraints on the natural language channel giving a way to explore how people and language models process code, and with natural language constraints on the algorithmic channel providing a way to bridge the machine's knowledge gap arising from asymmetry. For an example of using algorithmic constraints to learn about the natural language channel, consider equivalent expressions, which retain meaning on the algorithmic channel but have different natural language implementations. These can provide a controlled opportunity to understand how people process code and validate language model metrics used in training. All other things equal, when a language model finds something less surprising, how do people relate to it? We've found that people tend to prefer and comprehend that language code that language models find less surprising faster. This helps validate language models and code and provides a new task to compare the quality of language models and understand how programmers model predictable code. In the other direction, bridging the asymmetrical split of information can augment program analysis. For example, this tool Refinim from some of my co-authors refines types with natural language information. Built-in types can be imprecise, but variable names can hit at more precise conceptual types. These can be used to refine the existing types, which enables the type system to error check more effectively, in this case possibly preventing password data from leaking to another variable via programmer mistake. We can also consider that when information conveyed in each channel is different, it might indicate malicious or defective code. Some earlier work from others' authors has made use of this idea. From Azdroid, which found malicious Android apps by contrasting what text was presented to users with what apps actually did, to the code comment consistency work of Lin Tan, finding stale comments that conflicted with the written code that might need to be updated. We would like to push for a refocus on these kinds of analyses using more modern language modeling techniques and generalizing to use all the information in each channel of source code. In conclusion, we hope that this framework, acknowledging the asymmetrical nature of the channels and how they interact and constrain each other, will drive forward research taking a more holistic approach to code.